There's one other procedure that we have to see how it extends as we go from a function of one variable to a function of many variables, and that process is implicit differentiation. Now, just as a reminder, right, if you go back to functions that involve just two variables, x and y, you're dependent and you're independent, then this is an explicit form, right? Because the dependent variable is expressed explicitly as a function of the independent variable. But there are some equations that are expressed in this form, right? Where the dependent variable has not been isolated. This is the implicit form, right? And just to remind you of what the process is, let's do an example. Let's go back. So it's throwback whatever day of the week it is. I don't know, throwback Monday or throwback Thursday. But let's go back to Calc 1 and look at one of these implicit equations and just remind you of the process for finding the derivative of such a curve, right? So let's just do a little example here to set the stage, because again, this process that was first introduced in Calc 1, again, we're going to extend it to now these functions of several variables. So I won't make this one too complicated, but let's say you have something like this, where you have your x squared, and then you have your x times e to the y, and then let's say you have plus, 2 times the natural log of y, and then that's equal to 0. So let's say this is your implicit curve, and we want to find the slope, right, of this curve at any point at which it's differentiable. So we want to find dy dx. Well, there are different ways you can do it. Here is probably one of the more standard approaches. You're going to differentiate with respect to x. And the key here is to remember that even though the equation might not be explicit, what is implied is that y is a function of x. So this is, we're still saying that y is dependent on x. We just can't or have not written the equation in this particular form. So wherever there's a y, you have to interpret it as y of x. So when you do that, it makes, and you're doing your, say, you're computing a derivative, so you might have to use a product rule, but for sure you'll have to use the chain rule, because all of these are composites. You have e raised to another function. You have your ln of another function. So let's go ahead and differentiate term by term and see what we get. So we would have 2x plus, now here, since y is a function of x, and you have e to the y of x, and then you're multiplying by x, we have to use both the product and the chain rules, right? So product rule says 1 times e to the y, and then plus x times, and then when we differentiate the composite e to the y of x, we'll get back the e to the y, but then we have to multiply by the derivative of the inner function, and the derivative of y is going to be dy dx, right? And then we keep going, so plus 2 times, same idea. We have to differentiate using the chain rule here, so the natural log gives me the reciprocal, and then I have to multiply by dy dx, and then differentiating the right-hand side gives me 0. So now I have this implicit equation that gives the relationship between the slope and the variables x and y. So then the goal is, can we isolate dy dx? Yes, we can. And just algebra will help us there. So factor out a dy dx out of these two, and then move these two terms to the other side. And this is what we get. So plus 2y. And then now this becomes a minus 2x, and then a minus e to the y. And then therefore, our derivative with respect to x is negative 2x negative or minus e to the y all over x e to the y plus 2 over y, right? And we could go ahead and simplify it to get rid of the fraction, but mainly I wanted to remind you of this key process right here, because this is what we are going to initially replicate, but now let's say we have an implicit surface. So we'll have something like this, but now it will have a z, and the assumption is that z is dependent on x and y, right? So a surface, right, may be defined or described implicitly. So in other words, when you look at the equation for the surface, you don't see the z on one side and then your f of x, y on the other side. What you might see is this: x, comma, y, comma, z. So you'll see an expression, right, on the where you have all your variables are kind of mixed up together, and there's no easy or apparent way that you can isolate, let's say, z, get z by itself and express it in terms of x and y, right? So that's what it looks like. But what is implied here, so here is the implication, right? If, for instance, the question says, what is dz, the partial derivative of z with respect to x, or the partial derivative of z with respect to y, once you ask a question like that, it is implied then that z depends on both x and y. So even though the equation might not be written like this, this is what is implied, right? And then the goal, so our goal is to find what is the derivative of z with respect to both x and y, right? And the process is very, very similar. What we have to look for is anytime we're differentiating something with a z, we're going to end up getting either dz dx or dz dy, depending on our variable of differentiation, right? Just like over here, that whenever I differentiated something that had a y, because of the chain rule, right, I had to multiply by that derivative. The same thing will happen here. And instead of trying to write up formal steps, which you can do, but I think that the steps sometimes, because you have to, whenever you write down steps, it has to be very general. In this case, I think the steps almost cloud the actual process. So let's just look at some examples of this, right? And so let's take a look at number one. Let's say we have x cubed and then z squared minus 5 x y to the fifth z, and then is equal to x squared plus y cubed, right? Yeah, so we can see it. We can definitely see that this is in a form where, in fact, if you wanted to, you could put like all the variables on one side, and then you'd have something like this, and then your constant would be 0. Technically, the variables can be on any side, right? That's one of the things with the implicit form. It's not it's not very specific on what this would look like, right? But the thing that is, so I'm going to rewrite this just to indicate what is implied. So everywhere there is a z, actually what we have is z of xy, and then in this case it would be squared. And then we have minus 5xy to the fifth, and then again your z will also depend on x and y. And then on this side, we don't have any z's, so we just have terms that have our independent variables, x and y. So let's see, let's go ahead and compute the two first partial derivatives for this implicitly defined surface, right? So for dz dx, we're going to differentiate term by term with respect to x, meaning we will treat y as a constant, right? So differentiate with respect to x, but partially, right? So I'll just say holding y constant. Right. I guess formally we don't need to state it because that's implied. Anytime you have a partial derivative, it means that this is the variable that we'll differentiate with respect to, and all the other variables are held as constants. So let's see, what are we going to need here? We're going to need the product rule because we have a function of x here, so that's x cubed. But then we have another function of x here, because remember z depends on x, and that's being squared. So we're going to need the product and the chain rules. Similarly here, the y is being kept a constant, so that's fine. We can bring that down. But we still have a product that involves the 5x and then a function of x, which is our z, right? And then on this side, again, these will be relatively easy to differentiate. So let's go through and do our derivative with respect to x. So product rule here, first, the derivative of x cubed is 3x squared, and then multiplied by the second, so we'll have z squared. So I'm not going to continue writing the of xy because it gets really messy, but I want you to keep in mind that wherever there is a z, we have a function of that depends on both x and y, right? So derivative of the first times the second plus the first, so we got an x cubed, and then times the derivative of the second, and this is where we have to use our chain rule because we're going to bring that power down. We're going to keep the inner, subtract 1 from the power, and then the chain rule says I have to multiply by the derivative of the inner, and this is where I'll get my dz dx. Because when I differentiate z, right, with respect to x, I'll get dz dx, right? So this is why I wanted to do that example, kind of refreshing you or your memory about what happens in Calc 1, because it's very, very similar. It's just that now, again, you have different variables that you can be differentiating with respect to. So these two represent the derivative of this product, and then we keep going. Now with the minus there, I'm going to take out a minus, and also because the y to the fifth is a constant, I'm going to factor out the y to the fifth. That's my constant multiple. And then inside, I have to do a product rule again with the 5x times the z of xy. So product rule again, first term when I differentiate it is 5, bring down my z, and then plus first term is 5x times the derivative of z, and that's where I'll get another partial of z with respect to x. So that takes care of the left-hand side. Now the right-hand side, a lot easier. This is a regular derivative with respect to x, so this is 2x, and then y is being held constant, so we're going to end up with 0, right? And then our goal is to isolate dz dx. We want to find what that partial derivative is. So let's see, so we got 3x squared z squared plus, I'll put the 2 in front, so 2x cubed z dz dx, distribute the negative y to the fifth, so minus 5y to the fifth z, and then minus 5x y to the fifth, and then dz dx. And then on the right-hand side, we have our 2x. So subtract 3x squared z squared from both sides. Add 5y to the fifth z to both sides. So move these two terms over. And then factor out a dz dx out of the remaining terms. So we have a 2x cubed z minus 5xy to the fifth. And then we have our 2x minus the 3x squared z squared plus 5y to the fifth z, right? And then divide both sides by what I have in parentheses. So therefore, our partial derivative of z with respect to x is equal to all of this divided by what's in the parentheses. So our 2x minus 3x squared z squared plus 5y to the fifth z, all divided by the quantity 2x cubed z minus 5x y to the fifth. All right? And what happens is when you get these implicit derivatives, even of your surface, so you can see if I wanted to find, again, and we can still interpret this as a rate of change or as a slope of the surface in the x direction. If I wanted to evaluate this at a point, I would have to know not just the independent variables x and y, I would have to know the z value as well. So I would have to use the order triple to find, let's say, a rate of change at a specific point on this surface, right? But at least now we have the derivative that will give us that information. If we wanted to do, in fact, let me do this. I think I'm going to scroll this way. If I wanted to do the partial derivative or find the partial derivative of z with respect to y, it will be a similar process. Right? So for dz dy, again, we're going to differentiate with respect to y, and now we're going to hold x constant. So differentiate with respect to y, and then hold x constant, right? So this equation is still true, but the difference now is I don't need the product rule for the first term because the x cubed is a constant. So differentiating with respect to x, bring down the constant multiple, and then times. I still need the chain rule for this one, so I'll still write 2z squared, right? But I'm sorry, not z squared, just 2z. But then now when I multiply, I'm going to multiply by the derivative of the inner with respect to y. So then I end up getting dz dy. For the next term, we'll still have, I'll do that thing where we'll factor out the negative, but now since I'm holding x constant, I'll factor out we can actually factor out the 5x as well. So just put that outside, right? And then when we have to differentiate the product y to the fifth times z of x, y, z, then it's, again, we'll have to use our product rule. So the derivative of the first is going to be 5y to the fourth, and then times our z, and then plus the first, which is the y to the fifth, and then multiplied by the derivative of z with respect to y, and that's dz dy. And so I'll close those parentheses, and then now, again, the right-hand side is going to be a little bit simpler. There's no product. It's either, x or y. So this term now becomes 0 because we're treating x as a constant. So its derivative is 0. And then differentiating our y cubed with respect to y gives me 3y squared. Then we do the same thing. We're going to isolate and group. So let's just say this. So 2x cubed z dz dy. Now when I distribute the negative 5x, I'll get negative 25x y to the fourth z minus 5x y to the fifth dz dy. And then on this side, we just have our 3y squared. So now we only have one term to move over. So let's move over this negative 25xy to the fourth times z. That becomes positive when we move it over, and then let's factor out the dz dy. So we have 2x cubed z minus 5xy to the fifth, and then on this side we'll have the 3y squared, and then plus 25xy to the fourth z, right? And then our last step is to divide both sides by what's in the parentheses. And then we now have our partial of our surface with respect to y. So it's 3y squared plus 25xy to the fourth z over the quantity 2x cubed z minus 5xy to the fifth, right? And that is the formal process for doing the partial differentiation implicitly. Now, it turns out there is an alternative way you can do this. There's like a little formula, and I just want to show you where this formula comes from. So let's say we have one of these surfaces in general. So consider this. So let's say we have. So consider the g of x, y, z equals some constant. And what I want to be able to do is kind of write down, generally what would an expression be if I were to differentiate this implicitly, right? Well, the thing is, we can still think of this as our in terms of our chain rule. We can set up the hierarchy, because what we have here is we have z, even though it's not in this form, it is still dependent. We're still saying that it is dependent on x and y. And then x and y are not dependent on anything else. So if I were to express this using our chain rule, I would have to slightly rethink this and say, okay, well, again, because I don't have it in the form z of x, y, or f of x, y, this might not be the best form. But what I can do is I can say I have a function, and we're calling it g, and g depends on x, y, and z, right? That's what affects the points on the surface. So if I do this and say, okay, here's my x, here's my y, here's my z, and then I add this extra layer for z to say, okay, z depends on x and y. Now it gives me a way of differentiating this function g with respect to x and y. And let's see what happens, right? So let's differentiate. Let's first do it with respect to x. So differentiating with respect to x. So what that means is everything that ends up with, if I want to find the partial derivative of g with respect to x, what I need is, let's look at every part of this tree that ends with an x. Well, there are only two of them, right? So let me highlight this one. So I'm going to need this one. So that's a direct path there. And then there's another one here that is indirect, and it goes through z. So let's go ahead and label these with the partial derivative. So this one is dg dx. So that's one direct path, but then we have this other one where it's dg dz, and then this is dz dx. Right? So if I differentiate the left-hand side with respect to x, this is what I'll get. I'll get this term, which is dg dx, plus, so here's my or, the other one is dg dz times dz dx, right? So that's what I'll get if I differentiate the left-hand side. If I differentiate the right-hand side, because there's a constant, it doesn't matter if I differentiate with respect to x or y. This side here is always going to be 0. And if you notice what this does, this actually gives me a formula that involves the partial that I would want. So like if I want to find the partial derivative of z with respect to x, I can isolate this. So therefore, dz dx is equal to the negative of this. So the negative of dg dx over dg dz. So dg dz. And okay, so a simpler way to say it, if I use the subscripts now, this is saying if my surface is of this form, and I want to find the partial derivative of z with respect to x, what I can do is I can just differentiate this whole function, right? This whole expression here with respect to x, so that's negative, and then I have g sub x, that's what this is telling me, and then divide it by g sub z. So these are still partial derivatives, but it essentially gives me a formula that I can use to find this partial derivative, like a direct formula, right? So just looking at what's over here, if I differentiate with respect to x, then I would treat the y and z as constants and differentiate normally. And then here, g sub z, I would treat x and y as constants, differentiate with respect to z, and then when I set up this fraction, it will give me the required partial derivative. And something similar happens if I differentiate with respect to y. So differentiating with respect to y, again, if I look at my tree, now here are the y possibilities. So either directly there, and I'll go ahead and use the subscripts here for this one. This will be g sub y. Or I could go along that path, which is still my dg dz, so it's still this. But then go along this branch, and then that's my dz dy, so dz dy. So when I put that together, the chain rule says when I differentiate with respect to y, the left-hand side becomes dg dy, that's this one, plus the product of my dg dz, but then times dz dy. And then that still has to be equal to 0 because I just have a constant on that side. And then when I isolate so this is what I want. I want the partial derivative of z with respect to y. So therefore, dz dy is equal to the negative of this, right? My dg dy now over dg dz. So dg dz, which might be easier to express as a negative of g sub y over g sub z, right? So these two formulas, they are helpful. They are alternative formulas. You don't have to use them. If you like just using that formal approach that we developed way back when, in good old days of Calc 1, you can use it. But here are a couple alternative formulas that are helpful because they're direct formulas, right? They're direct formulas. And let me just show you how they're used, right? So let's say, so again, I'll pick a surface that's not too simple but also not too complicated so you can see how exactly to utilize it without getting overly complicated. So let's say we have a e to the x z squared plus y sine of z, and then minus 3 y x, or let me do it like this. xy to the fifth. And let's say that's our surface, right? Certainly not the simplest equation, but also not the more complicated one. And I'll just do one of these to kind of wrap it up. Let's say we want to find the partial derivative of z with respect to y, right? So all of this on this side is my g. So this is my g expression. And if I want to find the partial derivative of z with respect to y, I can use this formula. So I can differentiate this left-hand side first with respect to y. So let's do that. So dg dy. And when I'm doing this, because there are 3 letters on this side, we're going to treat x and z as constant, right? So we're going to treat x and z as constants, right? And let's see what happens. So this e to the x will come down, right? So because I'm treating the x as a constant and it's a multiple, so I'll have e to the x. Actually, wait, hold on a second. No. Actually, differentiating this with respect to y, all of this is 0, right? Because we're treating x and y as, x and z as constants. So this is 0. And then here, treating the z as a constant, so the sine of z will come down, and then the derivative of y with respect to y is 1. So we'll have 1 times the sine of z. And then with the minus, so again, remember we're treating x as a constant, so we'll bring down that minus 3x, and then we're differentiating our y to the fifth regularly, so we'll have 5y to the fourth. And that's what the partial derivative of this expression is, right, with respect to y. So it simplifies to the sine of z minus 3 times 5 is 15, and then we have x y to the fourth, right? So that's going to be here, right? And we'll all put it together. I'm basically just doing the pieces that I need. So I figured out what's going to go in the numerator. Now let's figure out what's going to go in the denominator. So dg dz. So same thing, we're going to differentiate this with respect to z. So in this case, we are going to we're going to treat our x and y as constants, right? So let's see. So now the e to the x will come down, times, and then when I differentiate z squared with respect to z, I'll get 2z, right? Keep going, plus, again, the y is now a constant, so bring down your y, constant multiple. Derivative of the sine of z is cosine of z. And then with the minus, now when I look at this, this entire expression, there is no z involved. So this whole thing is being treated as a constant, so its derivative is 0. So our partial derivative of g with respect to z is this, right? So let's write it as 2z e to the x, and then plus y cosine of z. So now, what does this mean? If I want to find the, let's say, for instance, the instantaneous rate of change of z with respect to x, right, my dependent variable, with respect to x, I have to take the negative. There's that negative sign in the formula. So the negative of this over this. So the negative of the quantity, sine of z minus 15xy to the fourth over 2z e to the x plus y cosine of z. Now if I distribute that negative, then this term will have a positive 15 coefficient, and then the sine will have a negative 1 coefficient. So I'll write it like this: 15x to the fourth minus the sine of z over 2z e to the x plus y cosine of z. All right? So, and if we wanted to do the partial derivative of z with respect to y, then what would happen is this would get flipped, right? So we would end up using this formula. Notice the denominator is the same. It's just a matter of if you're finding the partial derivative with respect to x, then you have to do your g sub x there. If you're doing your partial derivative with respect to y, you have to do your g sub y there, right? So this is just an alternative approach. I'm not saying that you have to use it. It's an alternative approach. If you're more formula-based, then this is a little bit more direct, as opposed to the previous method, which is more formal, where you go through and you differentiate term by term, treating your z as it is dependent on x and y, right? So there is implicit differentiation. And I will just say something, that this little process here is actually going to be very important coming up soon. So don't forget this. Put a little asterisk beside it if you're taking notes. And on that note, I'll see you in the next video.